general relativity step by step. Last time I was making the observation that if you have a vector that's quite large, in some sense, then the length of this vector is problematic because it cuts through your coordinate planes, which are themselves shifting and changing, and so the length of this vector is problematic. So I'm just going to consider small. Small enough so that this system here so that the coordinates they're not too badly behaved on a small length scale. If I define d to be the modulus of v, then I know that d squared equals the square root of v dot v. So, sorry, d equals the square root of that, but it's easier to consider d squared, which is just v dotted with itself. And I'm going to consider just small vectors here. So I've got v dot v, or d squared equals v dot v, equals delta x1 e1 plus delta x2 e2 plus delta x3 e3 dotted with itself, dot dx delta x1 e1, I forgot, yeah, plus delta x2 e2 plus delta x3 e3 equals sigma over I and j delta xi delta xj ei dot ej, or sigma over I and j, oh I don't need the sigma I and j because I've got the summation convention, delta xi delta xj ei dot ej, delta xi delta xj gij by definition. So what I'm going to do is that's d squared equals that. So what I'm going to do is to work out what gij is, equals ei dot ej, in a Cartesian coordinate system. Okay. Well, we know that E1, if I've got I equals 1 and 2, let's say 1, 2, 3, we know that E1 dot E1, I equals 1, 2, 3 correspond to X, Y, and Z, regular Cartesian. We know, well, there's two ways to think about this. We know that EX dot EX equals 1, and we know that EX dot EY equals 0 because they're at right angles. And we also know that EY dot EY equals 1. It's easier writing out the numbers, actually. It's easier writing out the numbers. We know, we know that EI dot EJ equals 1 if I equals J, and 0 if I is not equal to J. So that's the fundamental tensor, Gij, metric tensor. I'm showing my age here because when I learnt general relativity, it was called the fundamental tensor. And it's only later that it's become known as the metric tensor. Certainly the book I was given was called it the fundamental tensor. Fundamental. Equals metric tensor. Equals 1 if I equals J, and 0 if I is not equal to J. This is all in a Cartesian coordinate system, so a nice rectangular, steady, constant thing. We can also say that distance squared is from a point here, I'll just do it in 2 dimensions, x, y, to x plus delta x, y plus delta y. So that distance there is delta x, that distance there is delta y. We know that d squared equals delta x squared plus delta y squared. You'll notice there's no delta x, delta y term in there. Times 0, I guess. And this is saying the same thing, because if I write it in index notation, we've got delta x1 squared plus delta x2 squared plus 0 times delta x, delta y. If your coordinate system was a non-orthogonal one, you had an E1 bar and you need 2 bar which didn't cross at right angles, then you'd need to have a cross term here. And I'll show you an example of that next time. So what does that tell us? That tells us that Gij, well, we've got G11 equals 1, G12 equals 0, G21 equals 0, G22 equals 1 in a Cartesian reference frame. So that is my metric tensor in a Cartesian reference frame. It's super important, and I'm going to bang on and on and on about why it's important in subsequent screencasts. But for the moment, there it is in Cartesian coordinate system. It's just like an idea. It's not a matrix, but it's got 2 coordinates. It's got 2 subscripts. It's got an I and a J. All right, I'm going to stop there.